Welcome to AI for Good, the leading United Nations platform on artificial intelligence. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with over 50 UN agencies, and co-convened with Switzerland. The mission of AI for Good is to unlock AI's potential to serve humanity. As a multi-stakeholder platform, AI for Good advances solutions, standards, and skills. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging session. Boost your AI skills and elevate your career with the AI for Good Discovery Badge. Receive verified digital credentials that recognize your engagement in cutting-edge sessions, exploring how AI is being used to tackle global challenges. To see if a session is eligible, look for the blue badge banner on the right side of the video interface that activates at the end of each live session. Share your badge on LinkedIn and across your professional profiles, and check the AI for Good events webpage for upcoming eligible online sessions. Discovery Badge sessions are part of the AI Skills Coalition, ITU's global initiative to strengthen credible AI learning pathways and expand access to high-quality, trustworthy AI knowledge worldwide. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello! Today we are thrilled to welcome Dr. Kara Lamb, who is an associate research scientist in the Department of Earth and Environmental Engineering at Columbia University and also worked with NASA. She always had a hello?
Yes, please go ahead. We can hear you. Everything's okay.
A very strong focus on microphysical processes and aerosol-cloud interaction in her research, but I'm so sorry, the sound is lagging a little bit. Okay, thank you so much for your patience. And so she got her Master's of Science and PhD from the University of Chicago, and then was a research scientist at the Cirrus Center in the National Oceanic and Atmospheric Administration of the US, and participated in NASA and NOAA campaign. And now in her new research scientist research, she was able to focus on physics-informed machine learning methods, especially for cloud and microphysical processes, which I'm thrilled to hear about. The floor is yours, Kara, and thank you all so much for your patience.
Thank you. Just share my screen. And does that look okay?
This looks great on my end. Thank you so much.
Okay, Okay, great. Yes, today I'm going to be talking. I'm a research scientist right now at Columbia, and I'm a senior researcher in the Learning the Earth with Artificial Intelligence and Physics Center. And I'm going to talk today about physics-informed machine learning of cloud microphysical processes. So I just want to start by acknowledging many different co-authors who have contributed to this research. And I'll start with some motivation for this research, which is a better understanding of how we can represent cloud processes in atmospheric and climate models. And this is important because cloud and convective parameterizations, which are something which still limit our ability to predict future climate. So in a typical climate model, because we want to model the atmosphere or the Earth's over a large time period, we have to make some trade-offs in terms of like the resolution. And so a typical climate model grid box might be on the order of something like 25 to 100 kilometers, which means we have to be able to represent or parameterize all of these processes that are shown on the right in the atmospheric portion of the model. So these are things like shallow and deep convection, the radiative effects of clouds, as well as cloud microphysical processes, which is what I'm going to focus on here. And this is important because our current climate models are still limited in their fidelity, and this is related to things like the representation of cloud processes. So this figure comes from the Zelenka et al. 2017 Nature Climate Change paper, and it's showing across the ensemble of models in CMIP5 the spread in the projected average surface temperature from the year like 1850 up until the year 2100, when they're all run under the same emission scenarios. And we see this significant model spread at the year 2100, which is linked to that the net cloud feedbacks in the models. So if we can improve our representation of cloud processes, we can potentially reduce this uncertainty in our ability to predict like how much the Earth's climate will change in the future. And there's been a lot of research in the last like 10 years or since about the year 2018 on using machine learning methods to improve or replace parameterizations in atmospheric models and ocean models. And more recently, and there's been a lot of progress on that, but more recently, there's been what might be called this AI weather revolution, where people are moving away from like just modeling individual parameterizations in models and actually emulating the entire atmosphere, for example, to predict weather over the next 2 weeks. And this is just showing like how quickly that progress has been made in that area. This is showing, according to some skill metric, compared to sort of state-of-the-art physics-based weather numerical weather prediction models, like how quickly these AI weather models have significantly increased their skill. Up until like in the last couple of years, they've gotten to the point where they're actually more skillful than sort of state-of-the-art numerical weather prediction models. So that would since we can do a very good job of predicting weather just by using these data-driven machine learning methods, like do we still need parameterizations for like these different atmospheric processes? And I would argue that like, yes, we are still really interested in parameterizations. So this is for a number of different reasons. One is that AI models are mainly trained on reanalysis data sets, which themselves include things like parameterized processes such as cloud microphysics. So if we ever want to improve on the current AI weather models, we still need to improve our data sets and our ability to integrate observational metrics. And another reason is like this focus has really on this AI weather revolution has really been on the weather problem, which is sort of the short-term weather prediction, but climate is something which is much harder because we have to generalize outside of our training distribution, and we're also relatively limited in our training data compared to, say, this weather prediction problem. So for that, like having physical parameterizations really helps us to have some fidelity and also ability to like generate some synthetic training data sets. Also, if we want to be able to connect to laboratory and in situ observations to process-based models, like some of the work I'm going to show here, we really do need these physics-based parameterizations. And then finally, of course, we not only want to be able to predict with high accuracy, but we also want to be able to better understand the atmosphere and the climate and how it's changing. So for that, we really still need these physics-based parameterizations. And cloud processes in general are something which is really difficult to represent in models because they are very complex, they're nonlinear, and they also encompass a number of different scales. So here I'm showing on the left these cloud microphysical processes, and these are basically the way that liquid droplets and ice crystals inside of a cloud will interact with each other and evolve and grow as the clouds form. And like the natural scale at which we would want to represent these processes is using something like a direct numerical simulation. We're actually simulating individual liquid droplets and ice crystals, but to do this is very computationally expensive. So we're limited to like very small scales of the atmosphere that we can represent in this way. If we want to represent clouds in, say, a regional model, we can move to something like a large eddy simulation, but we're already at this scale having to make some simplifications in terms of our model or parameterization of the cloud microphysical processes. And then when we're talking about the climate scale, we are talking about having to also parameterize even the larger scale cloud processes like convection. And these are parameterizations are typically developed from models where we've already made some assumptions and parameterizations in terms of the cloud microphysical processes. So right now, we don't currently have a way that we can go across all of these different scales consistently with like the same type of model, but machine learning is something which can help us to like bridge that gap. And another challenge with cloud microphysics is like we still, even at the smallest scale, we don't fully understand all of the physics of these processes, especially across the range of different conditions that one might experience in the atmosphere. So particularly some of the processes that are related to the ice phase are particularly uncertain. We don't necessarily know the optimal way to take the cloud microphysical processes and represent these at the large eddy scale, and like what particular aspects of these processes need to be represented. And finally, when we get up to the climate scale, it's really a question of like what information is really important out of all of this complexity that we would actually need to represent at the climate scale in order to get the cloud processes correct. And like these are all challenges that machine learning can help us to address. In this talk, I'm mainly going to focus on ice cloud processes or cirrus clouds. And these are basically clouds that form high up in the atmosphere and have complex climate effects. So cirrus clouds are pure ice clouds. Here I'm showing some MODIS of satellite cirrus reflectances. This is basically just showing you where on Earth cirrus clouds form. So this is showing from the year 2005 up until the 2013, like where cirrus clouds would form on Earth. So like the white is basically where the cirrus clouds are forming. And cirrus clouds cover about 1/3 of the Earth's surface at any point in time. And in the mid-latitudes, they generally form above 8 kilometers in the atmosphere. And then in the tropics, we also get this band of cirrus clouds that form at the tropical tropopause layer, this cold region of the atmosphere above the tropics. And these are typically forming higher up at greater than 12 kilometers. And just depending on where the cirrus clouds form, they can have both a cooling and a warming effect on climate overall. So this is going to depend on the type, the location, the time of day, and the ice formation pathway, which is what I'm going to talk about on the next slide. But like in general, something like tropical cirrus can reduce outgoing long wave radiation, which can lead to heating of the atmosphere. So being able to model this complexity at the climate scale is important for getting the radiative balance of the Earth correct, but it's something that we still struggle to get because of some of these cloud microphysical processes that I'm going to talk about, as well as the interaction with some of the larger scale dynamics. So as I mentioned, there's a number of different ways that ice can form in the atmosphere, and it's actually a complex aerosol cloud interaction that's going to govern cirrus ice microphysics. So this figure comes from this 2012 Husen-Muller paper, which is basically a review of different ice nucleation pathways in the atmosphere. It's showing the supersaturation with respect to ice versus the temperature. And it's showing how ice can start forming in the atmosphere in these different temperature and supersaturation regimes. And the majority of ice that forms in the atmosphere is going to form through what's known as heterogeneous freezing. So that's when we have ice nucleation on a pre-existing solid aerosol particle. So an aerosol particle can be any type of small particulate matter that we have in the atmosphere, like mineral dust or potentially soot from forest fires. And heterogeneous freezing has a number of different ways that it can happen, as shown in this figure, but it's typically happening at temperatures that are greater than -38 degrees Celsius and supersaturations between 1 and 1.45 with respect to ice, so pretty much everything in this area. And it's going to be complicated. It's going to depend on the specific details and composition and size of the aerosol particles that are available. So there's like a many different details that have to be represented in models to represent these effects. In the coldest regions of the atmosphere, we can also have what's known as homogeneous freezing, nucleation of ice. And this is when ice, this is generally happening at colder temperatures less than -38 Celsius and supersaturations with respect to ice that are greater than 1.45. And this is when we no longer need a solid aerosol particle. We can actually have spontaneous nucleation of ice from aqueous aerosol particles. So that allows cirrus clouds to form in conditions that they might not otherwise have available ice nucleating particles. And the ways that the properties of the cirrus clouds that form through either the if we have ice nucleated homogeneously or heterogeneously are actually going to have sort of different overall effects on the clouds. So like for clouds that might form through homogeneous freezing, we'll generally have more small ice crystals, and these clouds will have a greater ice water path, which basically means they're thicker, and you generally would have greater cloud coverage overall. Whereas like if the clouds are forming mainly through heterogeneous freezing because we have a lot of solid aerosol particles around, then these clouds would generally have fewer and larger ice crystals. These ice crystals would have higher fall speeds, and the clouds would generally be like thinner. They have a lower ice water path and less cloud coverage overall. And there's a number of different things that we still don't fully understand in terms of our model representation of these microphysical processes that are impacting the cirrus cloud formation. So one is just the ice nucleating particles, like what types of aerosols can nucleate particles, what supersaturations and temperatures they nucleate ice well at, and their availability in different regions of the atmosphere. There's also still some uncertainties in terms of things like the water vapor supersaturation and its temperature dependence. So especially at colder temperatures, we might possibly have metastable cubic phases of ice that have different supersaturations than our typical hexagonal ice that generally forms at warmer temperatures. And finally, what I would focus on here a lot is the depositional ice growth process. So this is basically how the ice is going to continue to grow once it forms in the atmosphere through either one of these ice formation pathways. So I'm going to focus, as I said, on vapor deposition, and I'm going to talk about some ways that I've been using physics-informed machine learning and now generative AI to try to inform our understanding of this depositional ice growth process. And one of the main challenges with understanding microphysical processes in general and understanding how to represent them in atmospheric models is that the types of observations that we have from things like detailed airborne field campaigns, where we get the detailed information about microphysics that can really allow us to improve our understanding of these processes, these observations generally only provide information about the instantaneous atmospheric state, not the microphysical process rate that we're interested in representing in our models. And so as an analogy, you can think of this as like if we had players on a soccer football field at various points during a match, and we just had like snapshots of where they were at, like could you just from looking at where the players are at various times during the game, could you then infer the rules of soccer? And you can imagine this is like a very challenging problem, and this is like very similar to the types of challenges that we have to address when we use the available observations that we have and try to, in terms of informing our atmospheric models for some of these like specific cloud microphysical processes. So I want to argue here that we can use some of these new approaches to help us to get more information from the types of observations that we have so that we can really inform our atmospheric models. So I'll talk about some recent work using physics-informed machine learning applied to sparse laboratory measurements, where we can actually get the time evolution and look at individual ice crystals, but we only have a very, kind of a limited subset of measurements. And we want to try to infer a generalizable governing law. So I'm going to talk about using physics-informed machine learning applied to those measurements to try to get some generalizable governing law out of the measurements that we have. I'll also talk about some work on using some reduced order modeling of these detailed large eddy simulations that have been informed by the laboratory measurements to study how process rates can impact the populations of ice crystals, rather than just individual crystals, but rather how the whole cloud evolves. And then finally, I'll talk about some recent work looking at using generative AI applied to the atmospheric observations and physics-based models to infer probabilistic atmospheric histories from individual images. So we do get many different images of ice crystals from various airborne field campaigns, and we are trying to use generative AI to tell us something about how that particular image formed in the atmosphere. So going back to the soccer analogy, you can think of the first as looking in very closely at a couple of individual soccer players and understanding how they play the game and getting a lot of information about that. The second is more like taking the information that we learned from the individual players and putting that into a game or a simulation, and then from looking at how the players interact in that game, trying to infer something about the overall way that the game is played. And then the final is study is looking at sort of if we had an image of a soccer player at one point during a game, could we infer from where he's at right now, where he was in the recent past. So I'll start with this research on looking at physics-informed machine learning applied to the detailed laboratory measurements. And so, as I mentioned, the depositional ice growth process is basically how ice will continue to grow in cirrus clouds once the ice crystal has formed through either heterogeneous or homogeneous nucleation. And you can go to a cloud microphysics textbook like Prupakar and Klutz and write down this ordinary differential equation, which basically tells us how the mass of a single ice crystal will change as a function of time. And this is known as the capacitance ice growth model. It basically is a electrostatic analog to a capacitor. So basically, this equation is going to depend on the shape of the ice crystal, how supersaturated the air is with respect to ice, and then this G function, which is effectively what I'm going to refer to as a transfer coefficient. So G has, typically it has two different terms. One is related to the molecules to the surface of the ice crystal, and the other term is related to heat released when the molecules deposit on the surface. And there's still some uncertainties about this expression, though, especially in particular. There's this parameter which is known as the deposition coefficient. And this deposition coefficient basically tells us how efficiently water molecules attach to the surface of a growing ice crystal. It's typically been assumed to be a constant value, although there's recent work that demonstrates that it has a saturation and temperature dependence to it. And this deposition coefficient is important for not only just telling us how efficiently ice crystals can grow, but it can also be used to parameterize the shape of pristine ice. So when ice forms in the atmosphere, it forms in these different types of habits or shapes. And by parameterizing the deposition coefficient differently on different facets of the ice crystal, we can actually model represent different shapes of ice in our atmospheric models. The reason why this seems like a relatively basic and simple equation, but the reason why it's been very difficult to understand this, the functional dependence of this expression is that the early growth of ice is something which is actually very difficult to observe experimentally, and ice crystals are also undergoing various surface transformations. So you could use something like a molecular dynamics simulation to get a very detailed understanding of how a single ice crystal might grow. But what we are interested in representing in our model is effectively a parameterization of these processes in general. So you can think of this expression as sort of a parameterization of many different possible surface transformations that the ice crystal might undergo. And then for the sake of what I'm going to show later, we can like theoretically derive a kind of continuum limit where we have no surface effects, and we assume the ice crystal is spherical, and I'm going to call that GC. So that's basically the theoretical limit for G and that under those assumptions. So the data set that I'm using here comes from a series of laboratory experiments in the levitation diffusion chamber. And these come from Jerry Harrington's group at Penn State. So these are basically single ice crystals that are grown at constant temperature and supersaturation. So here I have a data set of 290 experiments. That's just showing the saturation with respect to ice and the temperature at which each of the individual ice crystals were grown. And we have both heterogeneously and homogeneously nucleated ice crystals. And what they observe in the chamber is the mass of the ice crystal as a function of time relative to its initial mass. So we get these mass time series. And so basically the question is like, from these initial conditions and these mass time series, can we go back and determine the functional dependence of this expression? So I'm going to use a physics-informed machine learning method to do this. I'm going to start with the ice growth rate from theory, and I'm going to replace what we don't know in that expression with a neural network. So this neural network is basically a function which takes in the saturation and temperature, and then given the weights of the neural network, it's going to predict a value for alpha in this case. I'm also going to look at a weaker version of this physics-based constraint where I try to fit that entire transfer coefficient relative to its continuum limit. And in that case, it's taking in the saturation, temperature, and mass, and then given the weights of the neural network, predicting a value for G over GC. In order to integrate over this expression, because what we actually observe is the mass time series, not the growth rate, I'm going to use this neural ODE approach. So this is basically a method where you can integrate neural networks with typical ODE solvers so that you can effectively learn the functional dependence while also integrating over an unknown function. And so I'm going to use this library to torch from this particular paper to integrate over this expression. And then in order to learn the unknown physics in the function, I'm going to minimize the distance between the observations from the laboratory and the model by optimizing the neural network weights for the strong and weak constraint, in each case using stochastic gradient descent. So that means that the trained neural network then has basically learned the unknown physics in that expression. And then I'm going to try to come up with a function that describes what was learned by the neural network for each case using symbolic regression on the trained neural network. So this is basically using a genetic algorithm to try to come up with a equation that describes the function that was learned by the neural network. So first, to validate the approach, I'm going to use a synthetic data set that I'm going to simulate mass growth at the same saturation with respect to ice, temperature, and initial mass as the 290 real experiments. And this is just to validate this approach. And so for the synthetic data set, I'm assuming a capacitance model for ice growth with the saturation and temperature dependent functional form for alpha from this Nelson and Baker 1996 paper. So this is just showing the alpha value for that saturation and for the saturation and temperature at which each of the ice crystals were observed from that Nelson and Baker paper. And then in order to get some like realistic noise on these synthetic data sets, I'm going to use singular spectrum analysis to detrend the noise from the real time series and then add that back on to the simulated time series. So I get some synthetic data set that has noise characteristics similar to the real data sets and looks similar to the real time series, but I know exactly what the functional form is because I've simulated these data sets. So then I'm going to optimize the node model to the ice mass time series with that known functional form. And then I'm going to do this across all 290 mass time series simultaneously. So this is just showing a subset of the optimized model. So the blue here is showing the synthetic time series, and then the red is the optimized node model once I've learned that functional dependence for alpha. And since I know the true value for the true functional dependence for alpha in this case, once I've optimized the model against the real time series, I can then compare what it learned for alpha against the true value from the literature. So this is just showing the alpha predicted from the neural network, from the trained neural network, and comparing that against the value from the Nelson and Baker parameterization that was used when I generated that synthetic data set. So you can see that what the model learns, it basically falls on the one-to-one line, which suggests it's doing a very good job of being able to learn back the correct functional dependence that allows it to like optimize this expression against the synthetic observations. So it's a little bit more complicated when I apply these approaches to the real observations, because in this case, we don't have any ground truth for what the functional form is. We're actually trying to determine what that functional form is. And we don't necessarily have a single functional form that fits every single mass time series exactly. So I'm just, again, showing a subset of the time series and a number of different optimized models, so both the a number of different lines that show the different models as they compare to the real mass time series. So in order to determine which model works best, I'm going to compare look at some different metrics for how well each of the models fit the mass time series across all of the experiments. So I'm going to look at a model where I have basically the pure capacitance model, so just assuming this theoretical limit GC. I'm also going to look at the parameterization from the literature for alpha for Nelson and Baker, then the strongly constrained model where I've just fit alpha, and the weakly constrained model where I'm fitting this more of the physics using a neural network, assuming we know less of the physics. And I can look at the mean squared error loss between these different models and the first 500 seconds of the mass time series, and lower value is better here. So this, I basically trained this on only the first 500 seconds. So I can also look at how well the models are able to extrapolate to the rest of the time series. So that's the second column here, the mean squared error loss, when I extrapolate longer in the data, when I allow the models to fit more of the time series. And then I can also look at which of these models does the best in terms of fitting individual time series. So some of the models fit better on various ice crystals than others. But across all of these metrics, this weakly constrained node model performs the best across all of the experiments, and it also best fits the majority of individual experiments. So we can then ask, what did we actually learn about the physics of ice growth? We have a model that now fits better, but I want to learn something, I want to understand why it's doing a better job at fitting the data than some of the other models. So I'm going to look at the functional dependence that was learned for G that's contained in that trained neural network. So this is basically showing what G looks like compared to GC, that theoretical limit. And the color here is the mass of the ice crystal. And then I'm also coloring it by whether they're homogeneously or heterogeneously nucleated ice crystals. And so we don't see a lot of difference between the two different ice formation pathways, which suggests that the depositional growth process is not necessarily controlled that much by the initial nucleation mechanism. But we do see that there's some dependence on mass that's not evident in the theoretical GC. And this suggests that there is a suppression of growth when the ice crystals are small, which is consistent with what has been known in past literature. And I can then try to come up with a symbolic expression for what was learned, what's this functional dependence, using the Peiser library to get a learned functional form for G relative to GC. And so I can come up with this functional form from Peiser. And then I can compare this functional form from symbolic regression with the functional dependence from the neural network. And it does a pretty good job of matching that learned functional dependence. It's a little bit more complicated in terms of determining which functional form is the best, because symbolic regression actually doesn't just give you a single proposed functional form. You actually get many possible functions, you get the Pareto front of various functions with different complexity that can all do a pretty good job of fitting that particular functional form. So I'm just showing a number of different discovered equations from Peiser. And we can look across all of these expressions, and we do see that they depend on G, C, and M, but we don't see much dependence on the saturation with respect to ice and temperature, except for in the most complex expressions. And some of these different equations will work better than others on different evaluation metrics when comparing against the levitation diffusion chamber experiments. But as far as improving our atmospheric models, what we're interested in is not really how well it does on the data set that these equation this equation came from, but rather like how well might these expressions generalize to new, fitting independent and new observations of depositional ice growth. So for that, I'm going to look at a series of experiments, compare these models against a series of experiments that were done in the AIDA cloud chamber. So these are very different experiments than the levitation diffusion chamber experiments. This is basically a large chamber where they can simulate atmospheric processes, such as cloud formation in the atmosphere. And this is from a series of experiments that we did during my PhD at the University of Chicago, where we simulated cirrus formation over a range of temperatures in the pure ice regime. And so in AIDA, we actually have changing conditions of saturation and temperature, unlike the levitation diffusion chamber experiments. So this is showing for the 48 experiments from the isocloud campaigns, the saturation with respect to ice and the temperature range for those AIDA experiments in red. And then I'm showing a comparison with the levitation diffusion chamber experiment ranges. And those are the like little black dots that are representing the levitation diffusion chamber experiment. So we have colder temperatures as well as like more supersaturation conditions in AIDA. So I can take, so in AIDA, basically the way these experiments work is they are adiabatic expansion experiments. So they basically remove air from the chamber. So we see this drop in pressure. This is an individual experiment I'm showing the time series for. And then because the air has been removed from the chamber, it causes the air inside of the chamber to adiabatically expand and then cool. So we see a corresponding drop in temperature. And that temperature drop causes ice to form on any available aerosol particles that are inside the chamber. So we see the number of ice crystals increase when the temperature drops inside of the chamber. And we can also monitor the supersaturation with respect to ice inside of the chamber, which is shown in black in this panel, as well as the ice water content, which is effectively the integrated mass of all of the ice crystals in a volume of air inside of the chamber as a function of time. So in order to compare these different proposed depositional ice growth models against the chamber measurements, I do need a parcel model with a bin microphysics scheme, and then I can use these different proposed depositional ice growth models and see how well they compare against the like evolving conditions of saturation and temperature inside of the AIDA chamber. And so I use, I'm showing here a this model where I'm taking in the temperature, pressure, and observed ice number concentration, and then predicting the saturation with respect to ice and the ice water content, given one of these proposed models, like this equation 8 that I'm showing here. So the blue line is showing the model results for both cases. And it does a very good job of being able to fit this like particular experiment. And I can look also across a number of different experiments across different temperatures and supersaturations to see like how well these different proposed models compare in terms of the saturation with respect to ice and the ice water content inside of the chamber. And overall, that equation 8 does a pretty good job of being able to generalize well to like the majority of the experiments that we observed in AIDA. So this suggests that we're able to learn an expression that not only fits the levitation diffusion chamber experiments better, but can also generalize well to an independent data set of new or like a different set of observations and ones that are more challenging and that we actually have changing saturation and temperature in these conditions. So we're now doing so this research is now under review, and you can check out our preprint if you're interested. And we're also now expanding this to look at some new data sets from the levitation diffusion chamber experiments, some like new conditions for ice growth. I'll now talk a little bit about some research that we've been doing on looking at trying to think about how we might improve the representation of cloud processes using some ideas like reduced order modeling. So when we represent cloud processes in models, particularly larger scale models, we have to have very simplified bulk parameter, what are known as very simplified bulk parameterizations of these cloud microphysical processes. So if we think of like an ice crystal like forming in the atmosphere, like any individual ice crystal, it's going to have some very complicated thermodynamic history that's going to lead to that individual ice crystal that we observe. However, when we represent this in a cloud model, what we're doing is we're basically taking a like a single point in space and time in this Eulerian framework, and we're like basically keeping track of the bulk like across the population, some information about, say, like the size of the ice crystal or its density. And then we're looking at how we're coming up with a way to parameterize how the instantaneous thermodynamic conditions would change these bulk properties of the populations of ice crystals at that particular space and time point. So we have to come up with a lot of we have to make a lot of trade-offs in terms of how we represent this complexity of these microphysical processes. And there's a number of different like approaches to do this, but mostly like in the larger scale atmospheric models, we're using these bulk representations where we're effectively making some assumptions about the, we're keeping track of the moments of these distributions, and we're just coming up with some parameterizations for how these different process rates would impact the moments of those distributions to the next model in the time step. We can also do some approaches like using bin approaches where we're like discretizing those particle size distributions. More recently, there's been a lot of research on using these Lagrangian particle-based approaches. These are actually not keeping track of the like sort of Eulerian like space, like at each Eulerian grid box, like it's not tracking the populations, but it actually has like individual particles that are affected along with the flow field in the model, but we don't represent every particle. We represent some representative population and also keep track of their multiplicity of these particles. These are really like the state-of-the-art way, and we can directly connect these approaches to the cloud microphysical process rates like the depositional ice growth process, but the challenge is they're like super computationally expensive. So we're still really limited to the process level models for these Lagrangian based approaches, but they can be very good ground truth for trying to understand kind of the evolution of the clouds in general. So here I'm going to focus on some simulations from a Lagrangian superdroplet simulation of a cirrus cloud case from the Iceball Field campaign. And this was some simulations that were done by Kamal Chandrakar and published in this GRL paper, which was basically taking in the information from the depositional ice growth laboratory studies and putting in these parameterizations into these LES simulations with superdroplets and simulating how cirrus clouds form in the atmosphere. This is just showing the individual like trajectories of some of these individual super droplets in the simulation for these ice crystals. And what Kamal found in his study is that the thermodynamic histories of the ice crystals can actually exert a strong influence on the observed diversity of the ice crystals. So I'm going to show some work where we're building on the simulations from Kamal's study to try to see, like, in these LES simulations with the super droplets where he's simulating this entire cirrus cloud forming in this across this domain, like, can we actually find some simplifications in terms of like, we have all of this complexity in terms of like the individual crystals that are being represented and the trajectories they go, but can we actually find some reductions in complexity? And are there actually some like characteristic trajectories that we might see? So this is work that was led by Oben Sturm, who's a PhD student that worked with us at the Leap Center 2 summers ago through the Momentum Fellows program. And he looked at whether we can use k-means clustering to actually cluster these individual trajectories of ice crystals. So basically, he used the supersaturation history of the ice crystals over about 40 minutes of the simulation to see if there's sort of like representative histories that are specific, like smaller, like less complexity in terms of like if we can sort of find characteristic trajectories that the majority of the ice crystals are following. So we do find that there are these like 4 different clusters that he found using k-means clustering, and the like cluster 4 here is basically ones that are starting out. So we actually found that the even though he's clustering only on the supersaturation history, the other properties of the ice crystal actually are like strongly correlated with like the supersaturation history. So things like the size of the ice crystal, the altitude at which it's observed, as well as the effective density of the ice as a function of time. And so there are like a population of ice crystals that are very supersaturated with respect to ice. initially, and these are the very large ice crystals, but they're also sort of starting lower down in the simulation. And then we see there's also this like orange population, cluster 1. These are ones that are like forming and that are basically very small ice crystals that kind of just stay right around supersaturation with respect to ice of like 0. And this is these are all like generally at higher like positions in the cloud. So we do see that there's a lot of correlations between these different properties. And we can also look at how these different populations are evolving over the course of the simulation. So as I said, cluster 4 are these very large ice crystals. This is showing sort of like the initial stages of the simulation. And then these crystals actually, because they're very large, they actually fall out of the cloud very quickly. So over the course of the simulation, by the end of the simulation, like the last like size distribution, the last these ice crystals have actually shrunk a lot because they've fallen through the cloud and started evaporating below the cloud layer. And so if we look at, say, cluster 1, though, where these are very small cloud ice crystals, and they basically don't change a lot over the course of the simulation. So these are the ones that are just kind of like staying around in the cloud. And you can think of like cluster 2 and cluster 3 as kind of being some intermediate populations between those two extremes. So you could actually, so even though we found these 4 representative clusters, we can actually think of these 4 clusters as lying along a single like manifold, which so we found by plotting the PCA components, like this is basically the PCA of the first 2 principal components for the supersaturation histories, like these clusters kind of like lie along this spiral in this PCA space. And so by looking at that, we were interested in like maybe there's just a single parameter that we can fit to this spiral that can describe the majority of the variance that we're actually seeing in these trajectories. So we fit this spiral parameter to this like this to that. This is basically like unrolling that spiral and fitting a golden spiral to it, which is just like basically a single parameter for theta, and that's going to like tell us where it lies along that manifold. And then we can color the ice crystal trajectories by this theta parameter. So we can see that we do get this range of different theta parameters, and like the ones that are the ice crystals that are quickly sedimenting out of the cloud are have these very high theta values, whereas the ones that kind of stay around in this like higher cloud layer are ones that have very low theta values. So this isn't like a new parameterization directly for like the bulk parameterization of the cloud, but we can think of the fact like this is kind of pointing the direction of the types of variants that we might need to represent in a larger scale model if we think of like this entire model as being effectively what's at the subgrid scale in a larger scale model. It suggests that we could potentially just use like a single parameter that we're representing that we can represent the effectively how quickly these ice crystals are falling out of the cloud. So I'll talk a little bit about some other observations that we can use to try to learn more about ice growth processes. We do have many different images from many past airborne field campaigns using these cloud particle imager probes. These are basically probes that are mounted on airplanes, and they can basically take these stereographic images of ice crystals in cloud. So we get these 2D projections of these different pristine ice crystal shapes. And there's been a lot of these that have been now compiled into this cockpit database that has like 12 million CPI images from past airborne field campaigns. So I'll show some recent work where we've been looking at using generative AI applied to a subset of those images to try to actually infer how these a particular ice crystal might form based on its the history, the thermodynamic history. So here we're using data from the Crystal Face campaign, which was a campaign over Florida, sampling Cirrus, and we have 24,000 different ice crystal images. And this was work that was led by Georgia Nicolaou, who is and Catherine Friedels, and they were both students that worked with me last summer at LEAP through the Momentum Fellow in our EU program. And the idea here is that we're going to train a diffusion model conditioned on a particular ice crystal image that we observed and then use high-spit back trajectories reconstructed from campaign-specific WRF simulations with shape-aware ice and snow as ground truth to train that diffusion model. And what we're interested in is like, if you had this particular image, could you like determine like a probabilistic atmospheric history for that particular image using this diffusion model approach? So diffusion models work by progressively adding noise to a sample in the forward diffusion process, and then the reverse diffusion process is like basically learning how we can generate a sample of a given data distribution from noise directly, so that we're effectively learning this denoising process. And because these diffusion models are generative models, that they're effectively trying to learn that generative process for the underlying data distribution from a finite set of samples. So we're effectively trying to learn like what's the actual like data distribution itself. So how we're going to use this for the case of the ice crystal trajectories is that we're going to take in, we're not actually trying to train the diffusion model on the images directly. We're actually trying to learn to generate the thermodynamic trajectories. And by the thermodynamic trajectories, I mean the past temperature that the ice crystal experienced, its past relative humidity with respect to ice it experienced, and it's the pressure that it experienced over the previous number of hours. And basically to do this during the training process, we're taking in the thermodynamic trajectory from the high split simulations, and we're going to use the CPI image to effectively condition the diffusion model. And we're basically learning to noise and to denoise this thermodynamic trajectory conditioned on the CPI image. And during the inference process, we're going to then take in some Gaussian noise and use the trained diffusion model conditioned on the CPI image to generate a probable thermodynamic history. And we can actually get an envelope of possible thermodynamic histories associated with that particular CPI image, since we can like try, different like initial noise trajectories. And what the conditioning does here is it basically narrows down the possible like thermodynamic histories that might be generated for a particular ice crystal. So if we didn't condition the diffusion model, we're basically learning sort of the climatological trajectories for that aircraft field campaign. But when we condition on the CPI image, we're like basically finding a much narrow envelope of possible trajectories that are associated with that particular ice crystal image. And so this is just showing examples of the conditioned and unconditioned generation of the thermodynamic histories for one particular CPI image, where the blue is the conditioned diffusion model and the yellow is the unconditioned. So we're significantly narrowing down that thermodynamic trajectories associated with that image. So we can look at how well the diffusion model is able to generate the range of different conditions that the ice crystals experienced during their recent thermodynamic histories. And we're going to use the average continuous ranked probability score as a metric to do this. So we do, this basically tells us how an ensemble compares with a specific value, and a lower value is better. And this is basically showing the real versus generated distributions for the pressure, relative humidity, and temperature across these trajectories for like the population of ice crystals we were looking at. And we can also look at how this CRPS score changes over time when we go back farther in the past for the generated thermodynamic histories. And what we basically see is that we're more certain about the recent past in terms of like the temperature, relative humidity, and pressure. But the observed ice crystal morphology can narrow down the probable thermodynamic histories, and it's also most informative about the recent past, or the recent 3 hours. So we have also been doing some work, this is led by Joseph Coe, a postdoc who's working with me on using self-supervised learning to try to understand more about the distribution of ice crystal habits in the atmosphere. This is, so one thing that he looked at was looking at the, basically using using the embeddings from a transformer model to look at the cosine similarity between different ice crystal habits that are like the typical ice crystal habits that are identified by expert expert identification, just to see like whether that actually is consistent with like what's actually observed in the images themselves. And so you can see that we can look at like the in-class similarity as well as the between-class similarity for some of these different identified ice crystal habits. So what we're thinking about now is like how we can also connect these learned representations with the observed environmental variables like the saturation and temperature to actually go towards an improved and observationally constrained ice crystal habit diagram to better understand like how ice crystals will like form in the atmosphere under various conditions based on observations. So I don't really have time to talk about thinking about how we can improve the parameterizations at the climate scale, but we are also doing some work on looking at investigating the sensitivity of large-scale observables to subgrid scale parameterizations using some perturb parameter ensemble approaches, like looking at in CAM, the community atmospheric model, like the sensitivity to different structural assumptions in terms of the ice microphysical parameterizations and how that impacts cloud processes. But that's sort of ongoing work, so I'm just going to like very skip to a conclusion slide. So as I mentioned, there's a lot of work that we've been doing on using physics-informed addressing how we can actually learn microphysical process rates from these different in situ observations. So I showed some work on using physics-informed machine learning to help us learn unknown physics from sparse laboratory observations. And using symbolic regression, we can discover interpretable functional forms for learned physics that generalize well to independent observations, which can help improve our ice cloud microphysical models. Using Lagrangian LES, these indicate that ice crystal diversity is strongly dependent on thermodynamic history, but the thermodynamic histories do demonstrate strong correlations across populations and suggest that many fewer degrees of freedom can be used to describe ice cloud processes at the larger scale. And then finally, generative AI is a promising approach for connecting in situ observational snapshots with the underlying cloud microphysical processes. And by conditioning on observed ice crystal morphology, we can significantly reduce the probable thermodynamic histories associated with atmospheric observations. So yeah, with that, I just want to say thank you, and I'm happy to take any questions.
Thank you, Kara. That was a fantastic seminar. It's so amazing to see how you educating the next generation of scientists while still working on climate problems, and also the scientific discovery part was really, really interesting. I'm going to start with a question from the public.
Okay.
So, can you explain what would be the obstacle to applying symbolic regression to the observations directly? And that's related to the first part of your talk.
Mm.
For the deposition
Yeah, I'm trying to
rate.
think like I guess the challenge is that like we're not like directly observing the part of the function that we're trying to learn. So like what we observe is like the rate of change of the mass, but what we're interested in is effectively learning this like growth rate and like its functional dependence. So like we effectively need to integrate over that. But it might be an interesting direction to explore. I'm like thinking also about like some other approaches like pins as well as like other ways to use like symbolic regression. So I definitely think there's like more ideas that could be pursued with these types of data sets. So yeah, to say like this is probably still something to explore, and like exactly how we might use these particular data sets and some of these like physics-informed machine learning methods. Right.
I have a directly related question on AI for scientific discovery. So when you did all this work and you finally got to optimal deposition functional form and you saw that it had this dependence in, 1 over A plus B over M. So what was the reward and how did it change your understanding of how deposition rate may directly depend on the ice crystal mass? What does that tell us about the process?
It does mean that there's like this there will be this sort of suppression of growth that when the ice crystals are small, which isn't something that's like we didn't know, but it was not easy to know how to translate that into like the model that like how we might model this like in say like a bin microphysics model or in the like Lagrangian superdroplet-based approaches. I guess it's like maybe a way that helps us to like more directly connect the like directly go from the observations to a functional form that we can then like represent in our models. But yeah, I think there are still ideas to explore here too.
And there's a question, another question from the public related to the methodology you employed. So that's much broader. Is do you think neural ordinary differential equation approaches like the one you deployed could help discover tipping point dynamics in the climate system?
Mm. I I think there's like definitely some interesting ideas to explore there. I mean, there's been a lot of work recently on looking at, well, this is sort of a different approach, but things like Koopman operators to look at like some of these tipping points. And I think that's a very interesting direction. I guess with the neural ODEs themselves, like I'm not sure if it like I'm not sure how to directly translate that, but I'm certain like there might be some interesting direction to pursue there, like in terms of like you know, integrating over available observations and trying to learn like the you know, dynamic expressions from observations. But
So, for example, do you expect it to be able to learn bifurcations in dynamical system, or would you be a bit cautious in such for such applications of neural ODEs? What has been your experience in how easy it was to set up?
hmm. I did have to think like a lot about the like one of the reasons I fit like G over GC is because it can be difficult to constrain, like it can be difficult to optimize if like alpha is something which we know is like between 0 and 1, so there's no problem there. But like having G be something which is purely unconstrained was problematic for using the neural ODE approach as I've used it here. So I think there are some limitations that like maybe other approaches might do better, but it seemed to work very well for this particular data set. But I do think like, yeah, I mean, there's, you know, also like neural operators and like neural PDEs, which can be like generalizations of these approaches. So I think there's definitely like ideas to explore and like a lot of work ongoing right now in the like scientific machine learning community on exploring how they can be like applied to, you know, like chaotic systems. But yeah, I'm not sure for like this particular application if it like generalizes well to that like chaotic case or not. But
So continuing with questions from the public, people are curious as to whether this physically informed neural networks modeling efforts can help better modeling supercooling processes, for example, and they refer to how these processes can be dangerous for airplanes. And so, I guess, do you have a general thinking on
I do think that they could be like very useful for some other like cloud microphysical processes. So one thing that I've started to think about is like how we might apply this approach to something like collision coalescence, which is a warm rain process. So like I think in general, when we have some of these like these types of problems where we're trying to determine a process rate and how we might represent that, I do think that like this approach could probably generalize well to that. I'm not sure about supercooling in general, but like there's there's other microphysical process rates. Like if we go back to this figure, there's many different microphysical process rates that we could potentially like think about like representing in this way. But
and then I have a question on the other part of your talk. I was really fascinated by how you were able to condition your diffusion model on the cloud particle images
yeah,
you
the CK
got.
images.
Um,
Yeah.
do you think do you think generally this is the way forward for more complex, for generative AI with complex multimodal data? Do you have tips and tricks on how to properly condition these diffusion model? It's really nice that you have this climatological prior, and then you can make it reduce the spread using the CPI image.
Um, I do think that like there's lots of interesting ideas to explore here, especially because you do get the like, ensemble of predictions rather than like a single prediction. And I think there's often cases where we're not just interested in like a single deterministic prediction for some of these processes. And there's still some uncertainties here because we're basically training this on high split trajectories, which themselves have some uncertainties, but at least like this is potentially taking into account some of those uncertainties and giving us like some idea of like what the spread might be for like a particular image. But like other ways this might be used, I don't know. I mean, I know there's a lot of work on using like diffusion models for like that, kind of like the weather prediction model for improving and things like what do you call it, data assimilation approaches. So I think there's lots of different interesting ways that people are now starting to use like these multimodal um, diffusion diffusion models for like these multimodal problems.
And maybe one last question to finish the talk, since you also mentioned you work on parameterization, which is so important for climate modeling. I guess it's more of a general question. I mean, microphysical modeling is so challenging. Observations are noisy, they come from
Yeah.
all kind of scales. You have a lot of inverse modeling aspects where you don't directly observe what you want to see. So do you really think the only way forward in that case is physics inform modeling approaches? And I guess going one step further, do you really think reduced order modeling and equation discovery approaches are an absolute must given the uncertainty we have with in situ and chamber observations? Or do you see the field moving in a slightly different direction? Like, what are your thoughts to connect the different scales and use
Yeah.
all these different observations? I know it's really hard, but I'm
Yeah,
curious to
I
hear your
didn't
thoughts.
show this slide, but we did this publish this paper in James, which is kind of like a perspectives on this kind of like, what's next for cloud microphysics parameterizations to machine learning. And there's just like as you said, there are many, I think when we wrote that paper, we found, there's like many different problems, but probably the two main ways that, cloud machine learning has made progress is on the bulk parameterization development side and then the interpretation of observations. So I think like there's ways that, things like differentiable programming can help us like bring together those like what we call more the top-down approaches where we're like using the very large scale remote observations and we can only like sort of infer from the remote observations something about the microphysics, as well as like these bottom-up approaches where we're starting with like individual process rates that we learn from laboratory studies and like trying to connect those and then maybe like including some unknown physics in these neural networks. I mean, I do think like these approaches where we're trying to kind of use physics to represent the large scale evolution of the model and then use like machine learning to learn what we don't observe, like this neural GCM approach is like one that's super interesting too. I mean, I think there's also just a lot of work that could be done on like making more community data sets available so that like some of these problems can be like attacked more. And I mean, I think another important point is like including things like uncertainty in all of this. But I don't know if I have like just like a single answer because as I said, there are many different challenges and problems with cloud microphysics. But
Well, at least you covered a lot of tools today on how to potentially address these problems, especially the conditional diffusion for the uncertainty part. So, in any case, thank you so much. I don't see any more questions from the public, so I think it's a great time to thank you again for
yeah,
joining our seminar. And
yeah, thank you for the invitation.
of course, thank you.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for good.